Okay, let's get started. So, today we're going to get into chapter 3, meromorphic functions. Anyway, she's very impressed by the tutors at the session. So I was wondering if one of you might be one of them. Okay, so before we start this, let me make a comment. So back when we proved that holomorphic functions were infinitely differentiable, you remember that the way we did it was to use the Cauchy integral. Well, one way we did it was to use the Cauchy integral formula, right? We said, well, look, this thing satisfies the Cauchy integral formula, and then we looked at the difference quotient, the difference between the difference quotient and then the formula for the derivative, and we saw that we could that went to 0. Right, that was the proof before the power series proof, right? Before the power series proof. Now you may recall, so one point I should have made at that point was that in fact what that proof showed. So the proof for the derivative form of the Cauchy integral formula the proof for the derivative form of the Cauchy integral formula actually showed that if you define a function f of z as as this sort of thing, as something of this form, where phi is a continuous function, then this f is holomorphic. Okay, because and for z not on z not on the curve, then f is holomorphic. And the proof that we did, you can do exactly the same proof. Okay, so what we used to show that this thing was differentiable was that it had this integral form, and then that and the continuity was enough to give us that that the difference went to 0. So in fact, if we create a function of this form, then it will be holomorphic. Okay, and this is a fact that we're going to use. We're going to need later today. Okay, so just a comment on the proof that we did some time ago. Okay, so today we're going to be talking about singularities. Singularities, namely so-called poles, removable singularities, and essential singularities. Okay, so these are like in terms of increasing complexity. As a singularity just simply means a place where the function isn't defined. Okay, so there will be 3 types of singularities, and we'll talk about each of them in turn. Not quite in this order, okay. So before we get, in order to get to singularities, we'll talk about we'll first talk about zeros. So, definition of a zero is pretty straightforward, right? It's just a place where your function is 0, right? So, your holomorphic function. It doesn't have to be holomorphic. Basically, we call z naught is 0, if a 0 of f, if f of z naught is 0, of course. Right? You all know that, of course. Okay. We want to talk about zeros of holomorphic functions. So say, okay, you have some omega a domain, and f a holomorphic on that domain, and f is not constantly equal to 0. So f is not the 0 function. Okay. So then, for any 0 z naught in omega, we have that there exists a neighborhood I think about it is what we call it. I'm just going to call it. There exists some neighborhood, around centered at 0 of some radius, in which f of z equals z minus z naught to the n times gz, where for some for some g holomorphic on the neighborhood, holomorphic and non-vanishing. On that neighborhood. Okay, so this is just a characterization of how what does a function, what does a holomorphic function look like near a 0? Okay, it says whenever you've got a 0, your function has to look like this, right? It has to look like some power of z minus 0 times the function that does not vanish near that 0. Okay. Okay, so and a lot of the things that we're going to do today are sort of like characterizing what the function will look like near the 0, near a pole, near a removable singularity, near an essential singularity. Okay, so that's basically what we're going to do today. Okay, so the proof is pretty straightforward. You say, well, look, your function is not uniformly 0, right? So what does that tell you? Since f is not uniformly 0, it's not 0 everywhere, you know that there must be some neighborhood. There must be some neighborhood, nRz naught, some punctured neighborhood, nRz naught. So remember, I put a star on it. I mean, it's a punctured neighborhood, what Stein calls a deleted neighborhood, a neighborhood with this not including the center. So here's z naught, right? It's everything but not including z naught itself. Okay, so that's my notation. Okay, so there exists some punctured neighborhood in which f does not vanish. Right? Right? Right. In other words, right? Z naught is not a limit point of the set of zeros, of the zeros of f. Right? Because if z naught were a limit point, then that would tell you that your function is 0 everywhere, right? And we assume that it wasn't 0 everywhere. Right? Everybody okay? Good. Right. So we know that there's some neighborhood in which f does not vanish, right? And then from here on in, it's just using the analytic the power series expansion, right? You say, well, look, so we know that take the power series expansion of f in that neighborhood. right? You get, f looks like, f of z looks like a summation a sub k z minus z naught to k, z naught to the k, from k equals 0 to infinity, right? And we know that that a naught is 0, right? So so now let n denote the smallest integer, the smallest natural number, such that an is non-zero, right? We know the first one, a naught is 0, right? So a naught is equal to 0. Let n denote the first one that is non-zero, right? And then you just factor those guys out, right? So that means that our series starts with an z minus z naught to the n and goes on from there, right? And so you just factor, you do sort of the obvious thing, you factor the z minus z naught out, right? Factor that out, and what's left over is g. That's basically it, right? So then, f of z is this, so f of z can be written as z minus z naught to the n times an plus 1, z minus z naught plus et cetera, et cetera. So we call this the sheet. Right? Yeah.
Is f entire in this proof?
No, we just it's just, I mean, it was just holomorphic on omega.
Okay.
It doesn't have to be entire.
I see.
Right?
What we need is that it's holomorphic on our little punctured neighborhood, right?
Yeah.
Okay.
Yeah.
Gotcha.
Yeah. Right. Yeah.
Right.
Okay.
Thank you.
Okay. So right. Okay. So and what's the point? This thing is holomorphic, right? You've got it. This thing converges. So G is, you have a power series expansion for G, so it's holomorphic, right? And it can't vanish because f doesn't vanish in the punctured disk, right? Right? In the punctured disk, this is non-zero, right? And right, and this has to be non-zero also. So neither of these things is going to vanish. So that's the end. Okay, so it's pretty straightforward. There's the first several proofs are nothing amazing. Nothing to write home about. Okay, everybody all right? Yes. Okay. Okay. So okay, we call just notation. We call n the multiplicity of the zero. Z naught. Just a remark. Okay, and it's clear that that's unique. It's the smallest integer for which the power series expansion is not zero. Okay. Okay, so now that we have zeros, we can talk about poles. So here's the Stein's definition of a pole, which is a little bit unusual, but it works. So you have f a function, right? And you have a point that is a singularity of f. Okay, and so if there exists a punctured neighborhood in which 1 over f, which you extend to have value 0 at z naught. So you take the function 1 over f, right? It's not defined at z naught because f is undefined at z naught. Okay, but you take the function 1 over f, and you extend it to have the value 0 at z naught. Okay, and then if there's a punctured neighborhood in which that extended function, that extended reciprocal function, is holomorphic, then we say f has a pole at z naught. Okay, so like for example, just a simple example, if f of z is 1 over z, right? If f of z is 1 over z, that's not defined, so it's undefined at 0, right? But if you look at 1 over f, well, that's z. It's still not defined at 0. But you extend it to have a value. You extend it to have a value at 0, namely 0, and you see that function is holomorphic, and so this guy has a pole at 0. Okay, makes sense. So you look at the reciprocal. Which is undefined at the 0, right? And then undefined at the singularity. And then you define it to be 0 there, and you check if that function is holomorphic. If that function is holomorphic if there's a function neighborhood in which that function is holomorphic, then you say you've got a pole there. Okay. Does that make sense? Yeah.
Is this function neighborhood centered at z naught?
Yeah. Yeah.
Wouldn't we want it to be holomorphic in the full neighborhood, not just the function neighborhood? The function with the extension?
Well, the thing is that you may have other singularities, right? So
Wouldn't you want, like, say, G defined to be 1 over f everywhere except Z?
Oh, yes, I'm sorry. So you're right, it's
be-
not phrased properly. If there's a punctured neighborhood,
Shouldn't it just be a neighborhood in which
yes,
the
thank
function?
you. Yeah, that's good. Thank you. Okay, so the theorem, we already characterized what functions look like near zeros. So we just use that characterization to describe what functions look like near poles, right? You say, well, if f has a pole at z naught, then there exists a neighborhood nr z naught in which f of z is z minus z naught to the minus n times some function h, where again h is holomorphic and non-vanishing on that neighborhood, and is unique again. Okay. And the proof of this is just, you say, well, 1 over f has a 0, right? So proof, kind of obvious. Right? If you have a pole there, right? F has a pole at z naught. So that tells you that 1 over f is holomorphic in some neighborhood, right? And has a 0 as E naught, right? So you just use the previous theorem, right? You know that 1 over f must be z minus z naught to whatever multiplicity that 0 is, times this non-vanishing holomorphic function, right? And then you just take reciprocals. So f of z is going to be z minus z naught to the negative n times h, which is still non-vanishing since g was. That's trivial. And again, we call this n the multiplicity of the pole. Okay. So one more completely obvious theorem. If f has a pole of order m at some point, then f looks like a power series that starts from some negative. Actually, sorry, this should be an m. This should be an n. Sorry. A minus n plus 1, z minus z naught, and minus 1, down to a minus 1, z minus z naught, plus some holomorphic function. So where this is holomorphic in a neighborhood of z naught. Right. Whenever you have a pole, you basically look like a like a shifted power series, right? Which is pretty obvious, right? Because your function is just you just have a power series here, and then you shift it by this. You shift it by this degree, so everything gets shifted down. Okay. So it's just like a power series that starts at some negative power. Yeah, Jane.
What are the negative indices? Like, are those? Is this just like a traditional power series?
Yeah. I could write it. I could write it like this maybe. K z minus z naught. The k as k goes from negative n to infinity. Say. Right. So these are the negative terms, and then this guy is from 0 onwards. Yeah.
Would it be from negative n to 0 though?
I'm sorry?
Or, wait, hold on. I'm tripping. Never mind.
It's okay. Okay. So, right, the proof. I hope the proof is obvious, right? You know that your function looks like this in some neighborhood, right? You know that your function looks like this, right, in some neighborhood, right? So, this is a holomorphic function. This is a holomorphic function, and so it has a power series expansion, and then you multiply it by this thing. All the terms get shifted, and you get this shifted power series. It's a proof obvious. Okay, so some terminology. This part here is called the principal part. f at the pole, z naught, and this coefficient has a special name. It's called the residue. Called a residue. Okay. There's some math joke, about Cauchy's dog leaving a residue at every pole or something like that. I don't remember. What does a dog have to do with, how are dogs like meromorphic functions? I don't remember. Anyway, something along those lines. Okay. Yeah. Okay. So yeah, and this thing, the residue, is going to turn out to be important in doing calculations. So it'll be useful to be able to determine the residue, and it's kind of a straightforward way to do it. So how does one calculate? How does one calculate the residue? So right. Let me just write it down. So if f has a pole of order n at z naught, then you can calculate the residue. The residue of f at z naught, that's the notation. The residue of f at the pole z naught can be obtained as the limit as z goes to z naught of 1 over n minus 1 factorial times the n minus 1th derivative of z minus z naught to the n times f of z. Right. So, for example, if you have a order 1 pole, right, then this just says, so for a simple pole, that is a pole of order 1, all you do is you take the limit of z minus z naught to the 1 times f of z as z goes to z naught, right? Because but you would only have, if it were a simple pole, then you would have this sort of thing, right? You would just have this. You multiply it by z minus z naught, you get the residue plus something that vanishes as z goes to z naught, right? For in that case, f is just going to be this thing over z minus z naught plus your holomorphic function, right? So when you multiply by z minus z naught, and then take the limit as z goes to z naught, well, this is gonna go to 0, right? And you're gonna be left with a residue, right? So, and this is just kind of the obvious thing, if you have right? If you have, right, if f has a pole of order n, then you know that z minus z naught to the n times f, right? You know that your power series, starts off from the negative n term, right? And so this is what's this going to be? This is going to be a sub minus n plus a sub minus n plus 1 z minus z naught plus the residue z minus z naught to the n minus 1 plus g sub z minus z naught to the n. Right, and then when you take the n minus 1th derivative, well, of course, all these terms are going to vanish, right? And you're going to end up with an n minus 1 factorial here, right? And so, and then these terms are all going to have powers of z minus z naught on them. And so when you take the limit as z goes to z naught, these terms are all going to vanish. Right? So these terms are all going to vanish, and you're going to be left with n minus 1 factorial times the residue. So that's what you want. Right? You take 1 over n minus 1 factorial times the limit of that. So is that all right? Yeah. Yeah. No.
If we haven't calculated the power series ahead of time, could we just start by taking the limit for n equals 1 and then for n equals 2 and so on until one of them exists, rather than knowing which n we want ahead of time?
Oh, that seems kind of awful.
I guess that's a fair point.
Yeah, yeah, yeah.
So do we usually just calculate the
yes
what the n
Well, I mean,
and then figure that out?
I mean, you don't. Well, what am I saying? You don't need to have the power series, right? You don't need to have the power series. You just need to do this, right, to get the residue. All you care about is in what follows. All that we'll care about is the residue. So you don't need to have the power series.
Okay. In order to figure out the multiplicity of the pool, do we just start taking the limits, assuming the
I see what
multiplicity
you
is
mean.
small,
Uh-huh.
and then just wait till one of the limits exists?
At least in the well, maybe this is sort of contrived, but in the examples that you'll see, it's sort of obvious what the multiplicity is.
Okay.
You can just look at it and see what the multiplicity is.
Okay, that makes sense.
So, yeah. Yeah. Okay. Okay, so let me just introduce a term here, meromorphic. So you have some open set in C, and you have a function on that open set. So if there exists a bunch of points, a sequence of points in omega, such that one, they have no limit point. They have no limit point. 2, f is holomorphic on omega outside of all those points. And 3, f has poles here. Then we call f a meromorphic function. On omega. So basically, this is, roughly speaking, it's just that, it's a holomorphic function with singularities, but all its singularities are poles. Okay, that's basically what meromorphic means. Okay. So, okay. Yeah. I think I've over prepared. Okay, so we're going to do something that's pretty straightforward. Not at all theoretically deep. but very practical. Something useful called the residue formula. And this is used for evaluating contour integrals. Okay, so here it is. Theorem. You have some open set. You have some function that is holomorphic on the set, but excluding some point. So I should just say it's meromorphic. Meromorphic on omega with a single pole z naught. Okay, so you've got your open set. You've got this one place where you've got a singularity. Okay, then you take any disk that contains z naught. It doesn't have to be centered at z naught. Then for any disk that contains z naught, whose closure isn't contained in omega, the integral of f about the boundary is 2 pi I times the residue of z naught at f. Okay, it's probably maybe it's just like that. Okay, so so the integral of the integral of the function around this curve is going to pick up the residue of the function at that pole. Okay, so that's really handy. You can evaluate integrals if you know the value of the residue, which you can obtain from the calculation we just put up, that limit thing we just put up. So the proof is again obvious. All of the proofs today are obvious. No, that's not true. A lot of the proofs today are obvious. Right? What's the point? You know that f is going to be this principal part. Plus a holomorphic function, right? And so when you take the integral, right? What happens when you take the integral around the curve of this? What happens? Well, each of these things has an antiderivative, right? These guys all have antiderivatives except for this guy, right? This guy doesn't have an antiderivative, right? We've seen already that when you integrate around the curve like this, you get 2 pi I, right? Which tells you it can't have an antiderivative. But in any case, what you get is a bunch of zeros, right? So all these initial terms have antiderivatives. This guy doesn't, right? This guy doesn't. But this is a holomorphic function, and so when you integrate it around the curve, you also get 0, right? And so what do we get here? We get the residue times 2 pi I. Right, which is exactly what we said here, right? That's it. So, and then this can be easily extended, so to the case where you have a curve. Yeah, you have a curve that's going around a bunch of poles. If you have a curve that's going around a bunch of poles and you integrate over that curve, what you're going to get is 2 pi I times the sum of the residues at those poles. Okay, and the proof is basically using the keyhole, right? So you create these little holes around each one of them. Create holes around each one of them, and then you see that the integral around this guy in the positive direction will be equal to the sum of the integrals around these guys in the negative direction, right? And so you get the sum.
So does that flip the sign then?
Wait a second. Let me get this right. I'm sorry. Sorry. You get that the sum of the integral around the outer guy plus the sums of the integrals around the inner guys.
Okay, yeah.
The sum of the integrals around the inner guys is 0, right? These guys are in the opposite direction, but
Yeah.
but
Okay.
then you move it to the other side, and the sign flips again. Thank you. Okay. Yeah. Okay. So, in any case, you can extend it. You can extend it to the case of multiple poles. Okay, so everybody okay so far? Modulo, everybody all right? Okay, so I don't think you're gonna like what we're gonna do right now, but we're gonna do it anyway. So we're gonna do some calculations using the residue formula. It's not the most interesting thing, but I think I should do them just because you'll see how these things work, and maybe a couple of tricks or things. I don't know. So we'll start off with an easy one. Dx over 1 plus x squared equals pi. Okay, so this is an integral. You could do it by some other method, but the cool way to do it is to use the residue formula. Okay, so what you do is you say, well, this is a real integral. What I'm going to do is I'm going to look at the integral of some meromorphic function. Okay, so over some contour. Okay. So you say, okay, look, if I let f of z be this guy, well, that's the same thing as 1 over z plus I, z minus I. Right. So this is a meromorphic function. And it has simple poles at I and negative I. Okay. So if we want to, so it has simple poles at I and negative I. If we want to look at the residue of this function at I, we know that that's the same thing as taking the limit as z approaches I of z minus I times this, times the function, right? And so we get 1 over 2I, right? So we know what the residue is. Okay. Okay, so now you say, well, we're interested. We're going to take. So let's say that here are the poles, right? I and negative I. So we're going to look at a contour that's that goes around this semicircle. Let's call it gamma sub r, where r is bigger than 1, so that we do contain the pole. Okay. So what do we know from the residue formula? We know that the integral of our function over gamma sub r is 2 pi I times the residue. Right? That is to say pi. Right, and we're going to use that fact to get information about this integral that we cared about at the beginning, right? And kind of in the obvious way, right? Like the integral, we're going to break this integral up into two parts, right? The part along the real line and the part along the circular arc, right? And as r goes to infinity, that will give us this. So that will give us information about this, right? We know that. We know that, right, the integral, if I call this CR plus, and I call this thing down here I sub r, right, we know that the integral of f over gamma r is the same thing as integral over I sub r plus the integral over CR plus, right, and that's equal to pi. Right. This guy here, of course, is just the integral from negative r to r of dx over 1 plus x squared. Right. So we get this plus this is equal to pi. Right, using from the residue formula. Right. So all we have to do suffices to show that the limit as r goes to infinity of this term is 0. Right. Because then we'll get the limit as r goes to infinity of this is pi, and that's what we wanted. Right? We wanted this integral to equal to pi. Okay. Right, so all you have to do is show that the limit, so we want to show that the limit of 1 over 1 plus c squared dz over CR plus goes to 0 as r goes to infinity. Okay. So you say, well, look, for z on CR plus, we know that the magnitude of z is r. Right? Magnitude of z is r, and we know that 1 plus z squared is going to be bigger than or equal to, by the triangle inequality, it's going to be bigger than or equal to the difference of the magnitudes. Right? It's going to be bigger than or equal to the difference of the magnitudes. Right? I can replace these by r, of course, but. And then for r big enough, bigger than the square root of 2, then we know that this is going to be bigger than r over 2, right? Because as r gets big enough, this 1 doesn't really matter, right? So we can ensure that this thing is bigger than some constant times r, right? Constant, some constant like 1/2. Okay. So what does that give you? That gives you that 1 over this is going to be bounded by the reciprocal 2 over r. Oh, sorry, r squared. Sorry, r squared. Yeah. Okay. So so what does that give us? So this integral here, when we take the magnitude of the integral, that's controlled by, right, by this bound on the integrand, right, times the length of the of the curve, right, and so we get, you know, some constant over r, right. Right, that constant doesn't depend on anything, right? It's just 2 pi. And so as r goes to infinity, then this thing goes to 0. Okay, so that's how we do it. Everybody, any questions? Any questions? Do you guys want to see another of these, or shall I just get back to the theory? Close your eyes for a second. Raise a finger if you want to see another example. Raise a finger if you want to just get back to the theory. Okay, put down your fingers. So, I guess the theory people will actually win if this were a vote, but there were a sufficient number of people who wanted to see another example that I think I should probably do another example. Not that interesting. I'm just going to do the theory. Sorry. Yeah, so yeah, I think I will just get back to the theory. I'm sorry. Okay, so yeah, because the other example, or the second example is has basically the same ideas as the first example. It's just slightly more complicated. Okay, sorry, I'm just going to go on. Okay, so now we're going to talk about removable singularities. Okay, so these are actually sort of like the less pathological, so they're less wild than poles. Removable singularity simply means that you can extend the function to a holomorphic function, right? So it's holomorphic in a neighborhood, but it's got this point where it's undefined. Okay, but it's possible to fill that point in such a way that you're holomorphic in the whole neighborhood. Okay, so that's what a removable singularity means. It's a singularity that you can remove and make yourself holomorphic there. Okay, so here's this theorem on Riemann's theorem on removable singularities. so here it is. So you have f on this open omega, as usual. So it's holomorphic with a singularity at z naught. Okay. So if f is bounded on if f is bounded outside of that point, then you can remove the singularity. So z naught is a removable singularity. I guess we should say bounded on a punctured neighborhood. Of z naught, yeah. Right. So you have your point. There's some neighborhood on which you're bounded. If you're bounded, then you can get rid of that. You can get rid of that singularity.
Is this theorem not true when f is just really different?
I mean, I think if we were to take just like the absolute value function but not defined as 0, then we can extend it continuously to 0 but not differentiably. Even though it's bounded in the neighborhood of 0.
Okay. Okay. So. Okay, so we're going to show that we can get rid of z naught as a singularity. Okay, so the way we're going to do it is by using Cauchy integral formula. So so take a disk. Take a disk centered at z naught. So z equals d of z naught. As usual, we'll let C denote the boundary oriented positively. Okay, so here's our z naught. Here's our disk. Then for each, so this is contained in omega. For each z in the disk, so you have some point inside there. Take a little disk around z naught. So take a keyhole around z naught. Okay, of some radius epsilon, and let's say that the width, as usual, we'll call the width of this little corridor delta, and the radius of the small circle epsilon. Okay. And we'll call that, so create this gamma delta epsilon contour. Okay, oriented positively. Okay, so we go this way, we go around the inside guy, and then we come out. Okay, so right, so by Cauchy's formula, we know that f of z can be obtained as the integral over that contour of f zeta minus z zeta. right? And then, just as usual, you let the deltas go to 0, so that the sides of the corridor cancel each other out. Okay. So what do we get? So letting delta go to 0, we get that f of z is the integral of over the outside guy, right, which was c, and then minus the integral over the inside guy. Right. Right, over this integral over the small circle. So we call, there's the outside guy, C, and then there's the inside guy, C epsilon. And I'm going to orient both of them positively and get this guy minus that guy. Okay, so, right, so what happens is, of course, that, well, look, right, f is bounded. So we have that, the absolute value of f is bounded by some m. Right. Now, the distance from z to z naught is bounded from below by some distance rho. Right. So what does that give us? That gives us that this guy here, right, 1 over 2 pi I, this, that is controlled by 2 pi epsilon over 2 pi m over rho, right? And so as epsilon goes to 0, then this thing vanishes. Right. This thing vanishes, and so what you get is this, right? That f of z is this over the exterior. Now, from the comment that I made at the beginning of class, this is a holomorphic function, right? This is a differentiable function, and it's defined at z naught, right? It's defined. This function is defined at z naught, right? So, this function is equal to f everywhere. It's equal to the holomorphic function f anywhere, and it's holomorphic at z naught. The right side is defined and holomorphic at z naught. So we have an extension of f to the entirety, right? In other words, the singularity was removable. Okay. Yeah, I think let's stop there.